Hello! In this video, I'd like to talk about the Krohn-Rhodes Theorem. Remember that we're interested in input to run maps for deterministic finite state automata. Functions that take in an input word and output the run of this automaton when we feed that input word into it. What the Krohn-Rhodes theorem allows us to do is to take these sorts of functions and decompose them as compositions of character-wise maps to translate between situations, and run maps for very specific finite state automata. As we feed in characters one by one to an automaton, each character acts as a function on the states. For instance, if we have a finite state automaton that looks like this, we'll let 0 be the start state, and it doesn't really matter what the accept states are for these automata, because we're not really talking about accepting or rejecting, we're talking about the runs of our automata. If we have this automaton, every time we read in a character, it applies a function to the state that we're in. And I'm going to want to represent these functions using these sorts of arrow diagrams. If we're in state 0 and we read an A, we wind up in state 1. If we're in state 1, we wind up in state 1. If we're in state 2, we wind up in state 1. If we're in state 3, we wind up in state 2. Now there's two extremes for what sorts of functions we could be looking at. We could be looking at a permutation. And so if we know what state we wound up in, and we know what character we just read, we can undo that function. That function's invertible, to figure out what state we were in before we read that character. On the other hand, with something like A, if we wound up in state 1, we don't really know what state we came from. And the extreme version of this is where these functions are constant functions. That's not the case here, but imagine if this 3 pointed to this 1 as well, then knowing that we read a character A would force us into state 1, and we'd completely lose information about the state that we were in before. So we'll say that a character or a function is a permutation if all information is kept. That is, if we can work out what state we were in before reading that character, before applying that function. If that function is invertible, or a permutation on the states. And the other extreme is we say that a function is a reset if all information is lost. That is, if it's a constant function. I'll say that an automaton is a permutation reset automaton if all characters act as either permutations or resets. So this automaton here is not a permutation reset automaton, because even though the character B acts like a permutation, the character A is neither a permutation nor a reset. It's somewhere in between. There are two special types of permutation reset automata. There's the permutation automata, where all characters are permutations. There's no resets. And because all characters are permutations, we can undo any sequence of characters, right? The functions corresponding to each character are all invertible, and so their compositions are invertible. And so we can actually run back the automaton as many steps as we want, just knowing what state we wound up in and what sequence of characters we just read. Another special type of permutation reset automaton is the plain reset automaton. It would be a little bit boring if all of the characters for an automaton were resets. That would just mean that the state at any one time is determined exclusively by the input that the automaton just read. That's really boring. The runs of those automata correspond to character-wise maps or shifts of character-wise maps, depending on what sort of run map you're looking at, and so those are really boring. So we want to add in as an option that reset automata characters can also act like the identity. They can also do nothing for the reset automaton. And so what that means is that the state of the automaton reflects the last reset input that the automaton read. And that's kind of interesting. That acts as like a piece of memory. Let me show you an example of a very basic reset automaton to get a sense of what these things look like and how they operate. This here is the 1-bit memory automaton. It has 2 states and 3 inputs. If we read in a 0, regardless of which state we were in before, we wind up in state 0. If we read in a 1, regardless of which state we were in before, we wind up in state 1. These are constant functions, these are resets. And if we read in an E, well, nothing happens to the state. So this is a reset automaton, a specific type of permutation reset automaton, and these characters are resets, and this character is the identity, which is perfectly allowable for reset automata. Let's take a look at what happens when we run an input through this automaton. This automaton starts in state 0, reads an E, doesn't change state again, reads a 0, and that forces it into state 0, but it was already in state 0. Then it reads a 1, and it forces it into state 1. It reads an E, and doesn't change state, reads a 0, and stays in state 0 for the rest of its run. Remember also that we're interested in truncated run maps, so let's get rid of this last character. So we have a nice length-preserving map. It's a little bit awkward, but we decided that truncated run maps with the last state removed as opposed to the first state removed, even though this is just the start state. This is kind of useless information. These sorts of maps are nicer and easier to study. The idea is that this automaton is kind of like a switch. When we read in an E, we don't do anything to the switch. When we read in a 0, we switch it to state 0, and when we read in a 1, we switch it to state 1. And that bit of information about the last reset character that we inputted is reflected in the state. And it stays that way as long as we're reading E characters, and then changes when we read the next reset input. This is a really essential reset automaton, so I'm going to want to give it a specific name, and we're going to come back to it. And this is the 1-bit memory automaton. So the Krohn-Rhodes theorem says this: truncated run maps for arbitrary automata can be written in terms of character-wise maps, so that we can kind of glue all of these pieces together, and then truncated run, I'm just going to abbreviate this as trun maps, truncated run maps for permutation automata and the 1-bit memory automaton. So in some sense we can kind of pull apart all of the reset behavior, even if it's like partial reset behavior like we see here. All of the non-invertible behavior of an automaton can be pulled out in like some sort of, it winds up being a cascaded composition and captured entirely by lots of copies of this 1-bit memory automaton. And of course, because I showed in a previous video that any causal length-preserving regular function could be written as a cascaded composition of character-wise maps and truncated run maps for arbitrary deterministic finite state automata, we can then write those causal length-preserving regular functions in terms of just these very specific functions composed together. And again, when I say composed together, I don't mean just composed together in a straight line. These are functions that can possibly take in multiple inputs if they correspond to automata that take in multiple inputs. And we're going to have to take advantage of that behavior in doing this proof. The sorts of compositions that you wind up getting when you do the Krohn-Rhodes construction look something like, which it's a little bit hard to parse. Let me show you what this looks like in terms of a parse tree. So it winds up looking something like this, although it's going to be even more helpful to look at it in terms of a diagram that looks like this. We're taking x and feeding it into all of these functions. These will correspond to automata, so we're feeding it into all of these automata. And then we're also taking the result of feeding x into our first automaton h and feeding the result into all of the later automata, g and f. And then for this middle automaton, g is reading in both the original input x and the output of the automaton h. So it's reading in all of the stuff before it, and then it's feeding its output to all of the automata after it, that is f. So the sorts of things that we're going to wind up looking at when we do this Krohn-Rhodes decomposition are going to be cascades of a bunch of different automata, again possibly glued together with these character-wise translation maps, where each automaton is fed in both the original input and the outputs of all of the automata before it, and then feeds its output to all of the automata after it. This operation of running automata in a cascade corresponds to something called the wreath product, which is related to the semi-direct product of groups. There's a small chance that the Krohn-Rhodes theorem might actually have really practical applications if it happens to be the case that it's really convenient to build circuits to calculate truncated run maps for permutation automata and one-bit memory automata, but somehow automata that have like this partial reset behavior wind up being really difficult or expensive to build. And so you could kind of build arbitrary automata run maps in terms of these pieces here. I don't know if that's actually going to wind up being the case. It seems like the real content of the Krohn-Rhodes theorem is in terms of some sort of algebraic decomposition. When we're studying finite state automata, we're really studying the underlying monoids, or really rather semigroups, because you don't always have to have an identity action for an automaton. So we're breaking that semigroup down as a wreath product of smaller automata, and then there's also character-wise maps which kind of correspond to semigroup homomorphisms. So the Krohn-Rhodes theorem kind of corresponds to the theorems that we have in abstract algebra, where we're breaking down finite groups into smaller finite groups, specifically semi-direct products of groups that can't be broken down any further. I want to show you a proof of this theorem. This is an adaptation of the proof in Ginzburg's algebraic theory of automata, and we'll do it in 4 steps. The first step is to break down truncated run maps for an arbitrary automaton with n states into a cascaded composition of the truncated run map for a permutation reset automaton and an n-1 state automaton. Our next step is to recursively apply that process to the n-1 state automaton, break that down into a permutation reset automaton and an n-2 state automaton, and just keep doing this iteratively until we wind up having a 2-state automaton. All 2-state automata are permutation reset automata. I'll let you check that. And so we'll have a way of writing the truncated run map for our original automaton as a cascaded composition of truncated run maps for permutation reset automata. We've broken down our arbitrary automaton into a bunch of permutation reset automata that are all feeding into each other in this sort of way. Step 3 is going to be to break apart those permutation reset automata into a pure permutation automaton and a pure reset automaton. So this will allow us to talk about truncated run maps for an arbitrary automaton in terms of truncated run maps for permutation automata and for reset automata. And then finally, we can break down those truncated run maps for reset automata into these 1-bit memory automata. Essentially, we're building up arbitrary memory storage from single bits. And so that'll be it. That'll be our proof of the Krohn-Rhodes theorem, breaking down truncated run maps for arbitrary automata into, again, we're going to need these character-wise maps to kind of glue things together, potentially, and truncated run maps for permutation automata and the 1-bit memory automaton. And we could actually break things down a little bit further if we wanted to. In the presentation of the Krohn-Rhodes theorem in algebraic theory of automata, they actually break these permutation automata down even further. Permutation automata we can think about as essentially just accumulators on arbitrary symmetric groups. And we can actually break those permutation groups down even further into finite simple groups, and then use these sorts of cascaded compositions to build up whatever we need here. But I don't know enough about finite simple groups for that to actually be a useful decomposition, so we'll just stop here when we've broken things down into just permutation automata. So step one of our proof, suppose we have some sort of deterministic finite state automaton. We need to decompose the truncated run map for this automaton into the truncated run map for a permutation reset automaton and an automaton with one fewer state. And the way that we're going to do that is really quite clever. We're going to use a permutation reset automaton to keep track of a state that this automaton is not in. So if we call our original automaton M, I'm going to call this new automaton M bar. It's going to have the same set of states, except it's going to have a different start state. The start state is going to be the first state that isn't the start state of the original automaton, so state 1 in this case. And the goal for each of these characters is that if we know that our original automaton is not in one of these 4 states, what's going to be a state after reading the character that the automaton is not in? Well, if we read the character A, we know that after reading the character A, we're definitely not in state 0. So this M bar automaton will say if we read a character A, regardless of which state we knew the original automaton wasn't in, we now know that the automaton is not in state 0. And we can do this sort of construction. We can create a function that's a reset. It's a constant function for any character here that isn't a permutation, that doesn't have full image. On the other hand, when we do have a permutation, we can just use that permutation. If we know that our original automaton wasn't in state 0 before reading a B, we know it's not going to be in state 3 after reading that B. Similarly, if we know that our original automaton wasn't in state 1 before reading a B, we know that it won't be in state 0 after reading that B, and so on and so forth. So this automaton here is going to be a permutation reset automaton. Each of the permutation characters of the original automaton is going to give us a permutation for this M bar automaton, and all of the other characters are going to give us resets for M bar. Let's take a look at a sample run for these automata. This W here is going to be our initial input word, and if we just run it through our original automaton M and truncate the run, so we remove the last state, the run looks something like this, right? We start off in the start state of M, that is 0. We read an A, that takes us to state 1. We read a B, that takes us to state 0, and so on and so forth. The truncated run map for M bar, on the other hand, is going to start off in the start state of M bar, that is 1. Again, we deliberately picked this not to be the start state of our original automaton. And we know that if our original automaton is not in state 1 and we read an A, then it's definitely not going to be in state 0 afterwards. If our original automaton is not in state 0, then it's definitely not going to be in state 3 after reading a B. And sure enough, it isn't, right? The state of our original automaton and the state of our M bar automaton are different in all of these cases. If our original automaton is not in state 3, after reading a B, it's not going to be in state 2. After reading an A, it's not going to be in state 0. And then after reading a B, it's not going to be in state 3. But again, we get rid of that last state. These are truncated run maps. So this automaton, M bar, is going to be the permutation reset part of our decomposition. For our original automaton, we're going to decompose it into this permutation reset automaton that keeps track of one state that this original automaton is not in at any time. And then we're going to have another automaton that's going to keep track of the rest of the information. And that new automaton is going to have one fewer state. Information theoretically, that makes sense, right? We're keeping track of one state that our original automaton is not in, and so it should take one fewer state to keep track of the rest of the information that's available. Although it's going to be a little bit tricky to keep track of that information. In order to get more clarity about what this decomposition is going to look like, I want to draw out the arrow diagrams for this entire input here, for our original automaton M. Right? Every time we read an A, it applies this transformation here to the state that our original automaton M is in. And every time we read a B, it applies this transformation here. So if we start at the start state of M, we can follow the run of our original map. Just following the arrows here tells us the sequence of states that our automaton visits. And again, our automaton M bar is going to keep track of a single state out of these 4 that the original automaton is not in. We start off knowing that it's not in state 1, which is not the start state of the original automaton. After reading an A, we know that it's not in state 0. There's no way to get to state 0 upon reading an A. After reading a B, we know that it can't be in state 3, and then can't be in state 2, and then after reading an A, we know that it can't be in state 0. So these are the states that we know our automaton is not in at any one time. That's the information that M bar is keeping track of. And now we're going to have another automaton, in this case a 3-state automaton, that keeps track of the remaining information. Out of the remaining 3 states, right, the states that are left over after we've gotten rid of the state that M bar says we can't be in, out of the remaining 3 states, which one of those is M in? I'm going to call this automaton M hat. So M hat is going to have 3 states. At the risk of being confusing, I'm going to call them 0, 1, and 2. And these are going to correspond to the 3 remaining states of M, once we got rid of this state here. Out of these 3 remaining states, M is actually in state 0 at this time. So we're going to want M hat to be in state 0 at this time. At the next moment of time, these 3 states are going to represent different states of our original automaton M. Instead of getting rid of state 1, which we did at this time, we're now getting rid of state 0. And so the 3 remaining states are 1, 2, and 3, which will have correspond to 0, 1, and 2 for M hat in the same order. And so we're going to want M hat to capture the fact that our original automaton M was in state 1, by having M hat be in state 0. The first available state here and the first available state here. At the next moment of time, we're still going to want M hat to be in the first state. Because again, when we get rid of this state here that M bar says that we can't be in, there's 3 states remaining, and M is actually in the first of those 3. At the next moment of time, again, 3 states remaining once we get rid of the 2 that M bar says we're not in. We're going to want M hat to be in the last of its 3 states. And then at this last moment of time, we're going to want M hat to be in the middle of its 3 states. So this is the desired run for our m hat automaton, the n-1 state automaton that keeps track of the rest of the information that m bar does not keep track of. We're going to want to be able to reconstruct from the run of m hat and the run of m bar the original run of the original automaton m. And again, the process of doing that is just going to be this in reverse. We'll write out the states 0, 1, 2, 3. We'll cross off the state that m bar says that we're not in, and then look to m hat to tell us which of the remaining states we're actually in. Right? This tells us that we're in the first of the remaining states, so m must be in state 0. This tells us that we're in the first of the remaining states, so m must be in state 1. The first of the remaining states, so m must be in state 0. The last of the remaining states, so m must be in state 3. And the middle of the remaining states, so m must be in state 2. So having the run of m hat and m bar allows us to, again, we'll use character-wise functions to, because this is a translation process, to reconstruct the run of the original automaton m. All that I need to do now is convince you that m hat is a real thing, that we can actually construct an automaton for m hat. So what sort of thing is m hat going to be? Well, it's going to be an automaton in our cascade. It's going to have access to the original input and also the output of the automaton before it in the cascade, specifically m bar. And with both of those pieces of information, we really do need both of those pieces of information. We need this information from m bar. M bar is actually keeping track of some information over time, and we don't want m hat to have to keep track of that information. It needs access to the information that m bar is keeping track of in order to be able to save that one state. First of all, we're going to have to know what the start state of m hat is, and that's really simple. We look at our 4 states, we look at the start state of m bar, and we get rid of that start state from that list. And then, since the start state of our original automaton m was the first state that remained, the start state of m hat is going to be the first of m hat's 3 states. The input characters to m hat are going to be a combination, one character from our original word w and one character from the truncated run map of m bar. So suppose that m hat reads in at some point the fact that we've inputted the character a in our original word, and m bar is keeping track of the fact that we were not in state 0 before reading that a. Well, m hat can be in one of 3 states, and we need to figure out how the state of m hat is going to transform when we're in each of these states before we read in this input here. And the way to do that is to, on a little piece of scrap paper, write out the states of the original automaton. Then cross off the state that m bar kept track of us not being in. Then sketch out the arrow diagram for a, for our original automaton. And then finally cross off the state that m bar is going to say that we're not in after we read this input. So if we're reading an input a, after we read that input, we're definitely not going to be in state 0. That's what m bar is going to tell us. And so this here, these are the states of m hat and the way that they're going to be transformed. The first state gets mapped to the first state, the middle state gets mapped to the first state, and the last state gets mapped to the middle state. So this is how m hat is going to transform its state when it reads in these 2 input characters. Let's do another example. Suppose that we read in a character A, and let's say that mhat keeps track of the fact that we were not in state 3 before reading that A. And again, the question is, how should we transform the state of mhat given this information? Well, again, we write out our 4 states of the original automaton M. We know that before reading that A, we were not in state 3, so we'll cross this out. And after reading that A, we know that we're not in state 0, because that's what M bar tells us. So the way that we need to transform the states of mhat are, regardless of which state we're in at the beginning, whether we're in the first, the middle, or the last of the remaining states, we're always going to wind up in the first remaining state. Let's do one more example. Suppose mhat is told that our original word reads in the character B, and m bar kept track of the fact that we were not in state 3 before reading that B. Again, we'll want to write out the states of our original automaton M. We'll want to copy down the arrow diagram from the original automaton. M bar tells us that we weren't in state 3 going into reading that B. And then we know how M bar works, we built it. So we know that if we start off in state 3 and we read a B, M bar is going to tell us that we're not in state 2 afterwards. And we just copy down what remains of the arrow diagram. The first state remaining gets mapped to the last state remaining. The middle state remaining gets mapped to the first state remaining. And the last state remaining gets mapped to the middle state remaining. And so this is the transformation we're going to see. If we started off in state 0 before we read this input, we'll wind up in state 2. If we started off in state 1 before reading this input, we'll wind up in state 0. And if we started off in state 2 before reading this input, we'll wind up in state 1. And that's exactly the transformation we saw here, right? When we read in a B and M bar told us that we weren't in state 3, we constructed this thing here, and it told us if we started off being in the first remaining state, we'll wind up in the last remaining state. So this is it. This is how you construct the automaton mhat, which keeps track of all of the remaining information. It's actually going to be, I don't think it's really helpful to show you a diagram for mhat, just because there's lots of different input pairs that mhat can read. Remember that at each moment of time, we're feeding in one character from W and one character from the run of M bar into our automaton mhat. So there's 8 possible combinations for things that we could enter into our automaton. But this is all we need. If we have our truncated run of mhat when fed in both the original input and the run of M bar on the original input, that's just the run that we actually saw of M bar. And then we can apply a character-wise reconstruction map that combines this run here with this run here to reconstruct what the run of the original automaton has to have been. And again, in order to reconstruct that data, we simply list out the 4 states of the original automaton. We cross off the state that M bar says we weren't in, and of the remaining 3 states, we look to mhat to tell us which of those is the state that our original automaton actually was in. So for instance, at this point, M bar tells us that we weren't in state 2, mhat tells us that we're in the last of the remaining states, and so M has to have been in state 3. So that's how the reconstruction map goes. Again, it's a character-wise map that just combines these two runs. So that's step one. Step two is really straightforward. We just iterate this process. We can write the truncated run map for our original automaton M in terms of character-wise functions, truncated run maps for permutation reset automata, and truncated run maps for automata with one fewer state. And so we just have to take this automaton here, break it apart as a composition of character-wise maps and truncated run maps for permutation reset automata and even smaller automata. We keep breaking them down, and then, fun fact, once we get to automata of size 2, which I guess is our next step anyway, because M hat has 3 states, once we get to automata of size 2, all automata of 2 states are permutation reset automata. You can just check that that's the only thing you can do. And when we do this breaking apart, it's a really long cascade of automata feeding their outputs to all of the future automata in the cascade, and reading in the original input and the outputs of previous automata in the cascade. This suffices to prove step 2, but I want to give you a sense of what these cascades actually wind up looking like. So specifically, in order to understand what this cascade is going to look like, we're going to want to figure out what happens when we break apart M hat. What does M hat bar look like, and what does M hat look like? In order to figure that out, I'm going to copy down this arrow diagram from up here down here. These are just the arrow diagrams that we figured out before. And in order to construct these, I really did need to take into account both the original input character and the value of M bar at any one time. I had to look at where these X's are to figure out how the remaining states would get transformed. So M hat bar is going to keep track of one of the states that M hat is not in, and I'll use different types of crossouts to represent them. So it starts off in the first state that M hat is not in. So it starts off, M hat bar starts off in state 1. This transformation here is not a permutation, so M hat bar is going to take all of the states to the first state that's not in the image of that permutation. Right? M bar, when we read an A, it takes in all of the states to the first state that wasn't in the image of A. Well, M hat bar, when we read in an A and a 1, is going to have to take in the state that we're in to the first state that's not in the image of this transformation. This next function here, when M hat reads in a B and a 0, it's actually just the identity transformation. So we know that if before that we're not in state 2, well, we know after that we're not in state 2. If our original automaton had a permutation, the bar version of that automaton has that exact same permutation. So here, if we know that we were originally not in state 2, then after reading a B and a 3, we know that we're not going to be in state 1. Because again, this is a permutation, so we just follow the permutation to take us from a state that we're not in before to a state we're not in after. And then finally, this transformation here, when we read in an A and a 2, is not a permutation. So M hat bar is going to take in all of the states and map them all to 2. Regardless of what M hat bar was keeping track of before, it knows for sure that after reading this input, after being transformed in this way, M hat is definitely not going to be in state 2. And so what remains, the states of M hat hat, Well, m hat hat is only going to have two states, and it's going to keep track of, for m hat, out of the remaining two states, when we get rid of the state that m hat bar tells us that we weren't in, out of the remaining two states, which one of them was m hat actually in. Here it's in the first, here it's in the first, here it's in the first, here it's in the second, here it's in the second. And again, we can work out the transformations of m hat hat just by copying this arrow diagram here. We know that the first state remaining gets mapped to the first state remaining, and the second state remaining gets mapped to the second state remaining. The first state remaining gets mapped, well, this is just the identity. The first state remaining gets mapped to the second state remaining. The second state remaining gets mapped to the first state remaining. And the first state remaining gets mapped to the first state, and the second state gets mapped to the second state. And remember that m hat hat is, we're going to have to feed this in a whole bunch of information. We're going to have to feed it in the input to our original m hat, which was both the input character and what m bar kept track of, and also the current state of m hat bar. So if the diagram for our original automaton transformation looked like this, we're reading in the input word w and we're passing it through the automaton m. Then our first step was to break the automaton m up into an m bar which read in the characters of w and then fed its output to an m hat which read in both the characters of w and the output of m bar. And then finally we took the combined output of m hat and m bar and ran it through a character-wise function that reconstructed the original run of our original automaton. M bar was a permutation reset automaton, so all we have to do is break apart m hat into permutation reset automata, and we do exactly the same breaking apart. In this dotted area, I'm going to draw the broken apart version of m hat. And again, we break it apart into an m hat bar that reads in the input to m hat and keeps track of a state that this automaton is not in. And then we have m hat hat, which reads in these inputs as well as the state of m hat bar. And then finally, the states, the outputs of these two automata are going to be combined together through a character-wise function to get the state, the output of this automaton here are m hat. And our breaking apart can stop here. M hat hat, because it's a two-state automaton, is a permutation reset automaton. It's actually a permutation automaton in this case, but in general it's going to be a permutation reset automaton once you get down to two states. But if we needed to, if our original automaton had more states, we could then break down m hat hat, and so on and so forth. Notice that all of the character-wise maps happen at the end. This is important in some of the different presentations of the Krohn-Rhodes theorem. One of the things that I like to do is actually, when we get down to a two-state automaton, to still keep track of a state that this two-state automaton is not in. Specifically, I'll use a different cross-out method, and that'll be our m hat hat bar, And in that case, the reconstruction map at the very end winds up being really nice. To reconstruct the original state of M, we simply write out the states of M. Step 1, we look at the information that M bar was keeping track of, the state out of these that our original automaton is not in, and we get rid of it. Right? These were the states of, I've erased it, these were the states, the run of M bar. Step 2, look at the states of M hat bar, which I've denoted here with crossouts. This tells us to cross out the middle remaining state. This tells us to cross out the last remaining state. This tells us to cross out the last remaining state. This tells us to cross out the middle remaining state. And this tells us to cross out the last remaining state. And then finally, the states of M hat hat bar, which are the things we crossed out here, tell us of the remaining two states which ones to cross out. So this tells us to cross out the second of them. This tells us to cross out the second of them. This tells us to cross out the second of them. This tells us to cross out the first of them. And this tells us to cross out the first of them. And so the states that remain are the run. I've erased it, but trust me, these are the run of the original automaton M. So these character-wise maps at the end, we can combine them into one big character-wise map. This one big character-wise map at the end is actually something relatively nice and simple. So that completes step 2. We've been able to break down the truncated run map of an arbitrary automaton. You have to generalize this proof, but I've shown you all of the things that you need to know in order to do that. We've been able to break down the truncated run map of any automaton as, again, it's a multivariable composition. It's going to be a fairly complicated composition, but it's a composition of a bunch of character-wise functions and truncated run maps for permutation reset automata. Step 3 is going to be to break apart those permutation reset automata into a permutation automaton and a reset automaton. Again, with some sort of cascaded composition. Again, I'll show you what this proof looks like for a very specific permutation reset automaton, and that example will include all of the information you need in order to generalize this to arbitrary permutation reset automata. So here I have a permutation reset automaton with one permutation and one reset. Let's define two automata. Our first automaton P is going to keep track of just the permutations that our original automaton sees. It's going to have the same alphabet as the original automaton. Its states are going to be permutations on the set of states of the original automaton. In this case, the set of states of the original automaton are the numbers 0, 1, and 2, and typically the collection of permutations on this set is denoted by S3. The start state is going to be the identity permutation. Remember, we're keeping track of the accumulation of all of the permutations we've seen so far, and so at the beginning we haven't seen any permutations, and so we just start off with the identity, or essentially no permutation. And then the transition function, we don't need to worry about the set of final states. These automata are just for their input to run maps. The transition function, if it sees an A, it composes, precomposes A with F. That is to say that if we see an A, we apply, A is a function, right? A is this function here. We apply this function to the permutations that we've seen already. On the other hand, if we see a B, well, that's not a permutation, and so we don't change the accumulation that we're keeping track of. In the general construction, if we see other permutations, we do something like this. We apply the permutation that we see to the current state, the accumulated value so far. And if we see a reset, we don't do anything to the accumulated permutation that we've seen so far. The other automaton we're going to want to have will keep track of the resets. So here's the thing. If we do a reset before or after a permutation, that's going to change how it influences the automaton. These things affect each other, and so we're going to want our reset automaton to keep track of the permutation that we've seen so far. It's going to have to read in, and again we can do this, this is just a cascade, it's going to have to read in characters from the original word and also the current state of the permutation automaton. The states for our reset automaton are just the states of the original automaton. The start state is just the start state of the original automaton, and its transition function looks like this. If we're in state Q and we read an A from our original word and an F from our permutation automaton, well, we read in an A, right? A is a permutation. And this automaton is just keeping track of the resets. So we don't need to do anything. We don't need to change the state at all. On the other hand, if this automaton is in state Q and it reads in a B from the original word and an F from the permutation automaton, well, that's the thing that we want to keep track of. And the way that we're going to keep track of that information is we're going to ask, what reset would we need to apply at the very beginning before seeing all of these permutations in order to have the effect of that reset? In order for this to work out, remember that B, in this case, is a reset to the state 1. Well, it needs to be the case that whatever state we reset to in the beginning, in our hypothetical, when we apply F to it, F is the accumulation of all of the permutations we've seen so far, we're going to have to wind up in state 1, because that's what the reset for B does. Right? In the actual situation, we've just seen a reset to B. And so this transition function just transitions into F inverse of 1. For the general proof, if we have a reset, then the transition function should just do F inverse of whatever state that reset resets to. So perhaps that's a little bit confusing, but let's see it in action, and hopefully this will make sense. So suppose this automaton reads in the word AAB, ABA. Let's first take a look at the truncated run map for P. We start off in the start state, the identity. We read in an A, so we apply the function A to the identity. That'll just give us the function A. We apply the function A again to get A squared, right? Just to apply A twice. The permutation automaton doesn't do anything if we read in a B. We read in a third A. It turns out that if you apply A to itself 3 times, you get the identity. Reading a B doesn't change anything. Reading an A would take us into state A, but we don't need to worry about that. So this is keeping track of an accumulation of all of the A's that we've seen so far, all of the permutations that we've seen so far. Now let's take a look at the run of R. Remember that R, we're feeding in both W and this run here. R starts off in the start state of the original automaton. And when we read an A in the first coordinate, it doesn't change anything about the state of R. So this A doesn't change anything, this A doesn't change anything. When we see a B, we need to look at F. So F in this case, right, the character from this run map that we're inputting is a squared. We need to take the inverse of that. Because a cubed is the identity function, the inverse of a squared is just a. And we need to apply it to the thing that b resets to, so 1. So we need to apply a to 1 to change the state here. Well, if we apply a to 1, we get 2. And again, the goal is going to be that when we apply this permutation that we see here to this state here, we get the current state of the actual automaton. We just saw a b, so the current state of the actual automaton is a 1. And it happens to be the case that a squared of 2 is equal to 1. If we're in state 2, we read an a. Again, a does nothing. We're in state 2, we read a b. We now have to do f inverse of 1. Well, f in this case, right, the value that we're getting from this run map is the identity function. And the inverse of the identity function is the identity function. So it's just going to go into state 1. And then finally, as I have alluded to, the way to put these pieces of information together is by simply applying this function here to the state here. So we apply the identity to 0, it's 0. We apply a to 0, that gives us 1. Apply a squared to 0, that gives us 2. A squared to 2, we said was 1. The identity to 2 is 2. And the identity to 1 is 1. And this here is just the run of our original automaton on this input here. And this sort of construction works in general. Because these two automata are not in just a straightforward composition, where the second automaton can only read the output of the first automaton, and they're not in parallel, that is, they get the same inputs, but they can't talk to each other, because we have this, and it only has to be a one-directional talking, P talks to R. P tells its state to R. Because we have this cascaded composition, we can untangle these permutations and these resets. So we simply take the really long cascade that we got from step 2, and we replace each permutation reset automaton in that cascade with this cascade of these two automata, and then a character-wise function to kind of do the appropriate translations. And that completes step 3. That allows us to write the truncated run map for any deterministic finite state automaton, which in turn allows us to write any causal, length-preserving regular function in terms of character-wise functions and truncated run maps for permutation automata and reset automata. The fourth and final step of our proof is going to be to break down an arbitrary reset automaton into some sort of composition of our specific 1-bit reset automaton that just has 2 states. Again, I'll show you how to do this for a specific example, and then you can generalize the proof. Suppose that we have an automaton with 3 states, A, B, and C, and the inputs, A, B, and C, act as constant maps, right? These are resets to state A, state B, and state C, and it also accepts the input E, which is just the identity. It doesn't change the bit stored in memory. So again, the state of this automaton at any one time is going to be the last character, A, B, or C, that we saw, ignoring any E's. Let's now define a 2-state automaton that just keeps track of whether this automaton is in state A or not. So this automaton has 2 states. It's going to start off in state 1. State 1 is going to indicate that we're in that state. Let's assume that A is the start state of this original automaton. So we'll start off in state A. For our automata that keep track of B and C, the start state will be 0 to keep track of the fact that this automaton didn't start off in state B or C. And then the transition function is going to be, well, if we read an A, we definitely go into state 1 to indicate that The original automaton, which just read an A, is now in state A. On the other hand, if we read a B or a C, we definitely go into state 0 to indicate that the original automaton is not in state A. And then finally, if we read an E, well, that doesn't change anything, so it shouldn't change whether or not the original automaton was in state A. And it's worth noting, this automaton here is just a recoding of the 1-bit memory automaton. And we can translate back and forth between this automaton and the 1-bit memory automaton just by using our character-wise maps to perform the appropriate translations. Again, we'll define similar automata to keep track of whether the original automaton is in state B or state C. And let's take a look at what happens when we run these on an arbitrary input. These are still the truncated run maps. I'm just abbreviating them a little bit to save space on the board. We know that our automaton A starts off in state 1, and I said that our automata B and C start off in state 0. When this automaton reads an A, it goes into state 1. When these automata read an A, they go into state 0 to indicate that we're definitely not in state B or C. When all of these automata read an E, the state doesn't change. When automaton A and automaton C read a B, they go into state 0, and automaton B goes into state 1. Again, we see some E's which don't change the state. We now see a C, automaton A and automaton B go into state 0. And then this B sets automaton B into state 1 and the others into state 0. And, well, I hope it's fairly clear what character-wise map to apply to each of these runs to get the run of the original automaton. Right? We just look at which of these automata is in state 1 and which are in state 0s. Whichever one is in state 1 is going to be the state that we want. And you can check that this is exactly the truncated run map of our original reset automaton applied to the input word. So this sort of composition here actually isn't a cascaded composition. We're running these automata on the input in parallel and then taking the outputs and combining them together with a character-wise map. So in our diagram notation, it looks something like this. And if we want to write it as a function, it looks like this. So that completes our proof of the Krohn-Rhodes theorem. We've been able to break down the truncated run maps for arbitrary deterministic finite state automata into just character-wise functions and truncated run maps for very specific automata. Permutation automata, which are essentially just accumulators on permutation groups, and this one-bit reset automaton. Somehow we're able to pull stuff apart, and because we still have this cascading going on, we're able to pull everything apart so that the permutation behavior and the reset behavior, the memory behavior, are separated from each other, and this one automaton is doing all of the reset work. All of the non-invertible stuff is happening in lots of copies of this one specific automaton. And again, because of what we showed before, this means that any causal length-preserving regular function it can be written as a composition of these very specific functions. So what's next? Well, I'd like to talk about arbitrary regular functions. What happens if we have a regular function that isn't causal? What happens if we have one that isn't length-preserving? What happens if we have one that's neither causal nor length-preserving? All of these generators are causal and length-preserving, so any composition of them is going to be causal and length-preserving. So what sorts of new generators do we have to add to our generating set in order to be able to compose, and again this is like a multivariable sort of composition, in order to be able to compose to produce arbitrary regular functions? So for now, let me know if you have any questions in the comments below, and I hope to see you in a future video.